For decades, dark matter has remained one of the most perplexing mysteries in modern physics. Although we cannot see or touch it, we know it's there. It exerts gravitational influence across the cosmos, shaping galaxies, bending light, and revealing itself through the movements of stars. Scientists estimate that dark matter makes up about 27% of the universe, while ordinary matter, everything we can detect directly, only accounts for a mere 5%. The rest is dark energy, another enigma altogether. But for now, let's focus on dark matter. The reason it's so elusive is simple. Dark matter does not interact with light. It doesn't emit it, reflect it, or absorb it, which means traditional telescopes are blind to it. But its gravitational pull betrays its presence, especially in galactic rotation curves, gravitational lensing, and the cosmic microwave background. Despite decades of effort, no one has detected dark matter particles directly. That's starting to change. In recent years, researchers have been developing some remarkably creative and unconventional detection methods. Methods that go far beyond the traditional underground detectors, filled with liquid xenon or germanium crystals. Among these novel approaches, two stand out not only for their ingenuity, but also for the radically different types of dark matter they aim to detect. The first one is being developed at the KAGRA Observatory in Japan. KAGRA, which stands for Kamioka Gravitational Wave Detector, is a facility designed to detect ripples in space-time caused by cataclysmic cosmic events like merging black holes or neutron stars. But now, scientists are repurposing this ultra-sensitive instrument for something else entirely: detecting ultralight dark matter. Let's pause for a moment. Ultralight dark matter is a hypothetical form of dark matter made up of extremely low-mass particles, like axions or dark photons, with masses far lighter than those of electrons, or even neutrinos. Because these particles are so light, they can behave more like waves than particles, permeating the universe like an invisible ocean of oscillating fields. If these ultralight particles exist, they could subtly affect the physical constants of nature. For instance, they could cause tiny fluctuations in the masses of fundamental particles or the strength of the electromagnetic force. These changes would be minuscule, billions of times smaller than what we can normally detect, but not beyond the reach of our most sensitive instruments. This is where KAGRA comes in. As a laser interferometer, KAGRA works by splitting a beam of laser light and sending the two beams down perpendicular arms, each several hundred meters long. At the end of each arm, mirrors reflect the beams back, and they recombine to produce an interference pattern. Any tiny change in the length of the arms, due to gravitational waves or any other disturbance, shifts the pattern. Now imagine ultralight dark matter passing through Earth and subtly altering the size of atoms or the local value of fundamental constants. These changes, although tiny, could cause the lengths of KAGRA's arms to fluctuate slightly in a way that's synchronized with the dark matter field S oscillations. Over time, by analyzing the interference patterns and looking for periodic signals, researchers might catch a glimpse of these elusive waves. But what makes KAGRA particularly suited for this kind of detection is its sensitivity and isolation. Located a kilometer underground in the Kamioka mine and cooled to near absolute zero, KAGRA is shielded from seismic vibrations and thermal noise. It's a near-perfect environment for catching whispers from the universe, including, potentially, the whispers of ultralight dark matter. This method doesn't rely on particles smashing into detectors or leaving telltale traces of radiation. Instead, it listens for the slow, rhythmic undulations of a cosmic field that stretches across space and time. It's an elegant and subtle approach, one that leverages the remarkable tools we've built for gravitational astronomy and turns them into instruments of particle physics. But as brilliant as this is, it still only addresses one corner of the vast landscape of dark matter possibilities. What if dark matter isn't ultralight, but instead ultra-heavy? That's where the second method comes in. Underwater acoustic detection. This idea is as audacious as it is fascinating. It proposes using vast volumes of seawater, essentially the entire ocean, as a detection medium for ultra-heavy dark matter particles that might weigh as much as a small grain of sand or even a pebble, yet be extraordinarily rare and fast-moving. The logic goes like this. If an ultra-heavy dark matter particle were to zip through the Earth at high speed, it would deposit a huge amount of energy in a very short time, essentially plowing through matter like a supersonic bullet. As it moves through seawater, it would heat up the surrounding fluid along its path, causing rapid thermal expansion. This sudden, localized heating would generate a pressure wave, a sound wave, propagating outward through the water. This is known as the thermoacoustic effect. It's the same principle used in some types of neutrino detection experiments, like the proposed acoustic neutrino telescopes. But in the context of dark matter, it takes on a bold new purpose. Now, detecting such an event would require an array of highly sensitive underwater microphones, hydrophones, distributed over a vast area, listening for short, impulsive acoustic signals. These signals would be incredibly brief, lasting just a few milliseconds, but they would have a distinctive shape and frequency profile. With the right signal processing and machine learning tools, researchers could distinguish them from background noise like marine life, ships, or earthquakes. Why seawater? Because it's abundant, transparent to sound, and acts as a giant detector that doesn't need to be built from scratch. The ocean provides an immense detection volume for free. All we have to do is listen. The challenge, of course, lies in filtering out false positives and building an infrastructure robust enough to operate continuously in such a harsh environment. But the potential payoff is huge. If even one ultra-heavy dark matter particle were detected this way, it would open an entirely new window into physics. It would confirm not only the existence of dark matter, but a type of it that is utterly unlike anything we currently consider in standard models. It would be a revolution. These two methods, KAGRA S-laser interferometry and underwater acoustic detection, represent two ends of the dark matter spectrum. One searches for feather-light particles using precise measurements of space-time. The other hunts for cosmic, wrecking balls crashing through our oceans. Yet they are united by a common philosophy that dark matter might be hiding in plain sight, detectable not by brute force collisions, but by the elegant interpretation of subtle signals in nature. They also exemplify a broader shift in the scientific community. As conventional detection methods yield no results, more researchers are turning to alternative models and creative strategies. This doesn't mean the old methods were failures. On the contrary, they helped refine our models and rule out many candidates. But now, it's time to widen the search, to embrace bold thinking, and to use the full range of tools that modern physics offers. Whether it's gravitational wave detectors, becoming particle detectors, or oceans transformed into vast ears, listening for cosmic impacts, the boundaries between disciplines are beginning to blur. Particle physics, astrophysics, oceanography, data science, they're all converging in this grand quest to illuminate the dark. And it's not just about discovering dark matter, it's about the spirit of exploration. It's about pushing the limits of what we can observe, measure, and understand. It's about asking questions that seem impossible and then building the tools to answer them. The coming decades will likely bring even more unconventional ideas. From using atomic clocks to detect oscillations in dark matter fields, to monitoring pulsars for anomalies in their timing, to employing quantum sensors capable of detecting the faintest perturbations in space-time. Each idea adds a new arrow to our scientific quiver, a new way to probe the fabric of reality. But whether we find dark matter next year or in 100 years, one thing is certain: the search itself is driving innovation in ways we never anticipated. It's teaching us to look at the universe with fresh eyes, to rethink the obvious, and to listen, not just for loud bangs in particle accelerators, but for the quiet harmonies and sudden whispers that echo through the cosmos. And who knows, the answer might already be all around us, embedded in the gentle pulses of a dark matter wave drifting through the KAGRA detector, or in the fleeting ripple of pressure from a silent particle streaking through the ocean depths. All we have to do is listen carefully and be ready to understand what we hear. Let me know if you'd like a shorter version, a French or Spanish adaptation, or a voiceover style for narration.